So the question I always asked myself when I was a young student was, why do some things dissolve in water and other things don't? Specifically, why do some ionic materials dissolve in water and others don't? Right? Aren't they ions? Aren't they supposed to separate in water and form aqueous solutions? But not all do. So are there guidelines that can help us understand which ones will dissolve and which ones won't? So we don't just randomly put stuff in a solution thinking it's going to dissolve and it really doesn't. So there are. So we're going to review them right now and how easy that is to determine that. So here's the chart that we're going to use to determine solubility of ionic salts in water. Now it's very simple to use. It looks like it's complicated, or it's not like a normal chart. It's kind of like a table. But let's see how it works. On this side of the chart, right here, these are all the ions that are generally soluble in water, no matter what they're bonded to. These ions here are generally insoluble in water, no matter what they're bonded to. So soluble, insoluble. Now there's always exceptions to the rule, and those are listed here. So for example, let's look at this acetate. Acetate is always soluble in water, no matter what it's bonded to, and there are no exceptions to the rule. So if you have like lead acetate, it's going to be soluble in water. Sodium acetate, it's going to be soluble in water. On this side here, we've got carbonates. Let's say we're talking about lead carbonate, magnesium carbonate, whatever, right? It's going to be insoluble in water, except for these conditions. And lead nor magnesium meet them, right? You need to have a group 1 element in the compound with the CO3, or ammonium, which is NH4. If you don't have those two, one of those two in there, then you're going to have an insoluble compound. Again, so let's see how it reads. So now, let's see how this is read. If you notice here, most of these things are all negative, and that means that they're the anion. Okay? Most of these are the cations, right? And these two are the cations. Cation means plus ion. Then we have a negative ion, right? So you should know that. So cation is the positive, and then the anion is the negative side. Now, when we do an ionic compounds all have the anion and the cation in a certain order. The cation always comes first. So if we were to split this down the middle, each one of these between the metal and nonmetal, then we could say, apologize if the line is a little on one side or the other, we could say that all of the sides on the left are all the cations. So whatever's on the cation side is listed on the left of the line. And then everything on the right would be my, let's change the color on that, is going to be my negative ion. And that's my anion, A negative ion. That's what anion stands for. And there we go. Okay. So how do we read the chart? We're always going to look for the anion first in our system. If we can't find it, then we go to the cation. So the first one is we're going to look for OH on my chart here. And here it is, hydroxide. Now, normally it says it's insoluble, right? But let's check the exceptions to the rule in case we meet that. When combined with group 1 ions, and H4 is not a group 1 ion, calcium, barium, strontium, which are group 2 ions, or ammonium, which is NH4, and there it is, there's the ammonium. So normally it's insoluble. Since it meets the exception, it's going to be soluble. So then we just write soluble right here. I'll put that in red. You go to the next one, potassium hydroxide, again OH. But potassium is a group 1 ion. So we're going to say that it is, again, soluble. Even though the OH is insoluble, Normally it's soluble. This one is soluble. Silver chloride, silver chloride. So we're going to look for the chlorine, and there it is. And normally it's soluble, but it's insoluble when we have bonded to silver. So now in this case, it's bonded to silver, so therefore this is insoluble. That's what IN stands for. Lithium carbonate. Again, where's the carbonate? Right here. It's normally insoluble, except for in group 1 elements. And group 1 is lithium, so therefore it's soluble. And you can continue down the road. Sulfur, sulfide, is normally insoluble, except when it's bonded to group 1 or ammonium. Magnesium is not a group 1 element, therefore it's insoluble. Barium phosphate, where's the phosphate? It's right here. When combined with group 1 ions or ammonium. Barium is neither a group 1 ion or ammonium, therefore this is also insoluble. Potassium phosphate, again is insoluble, and there it is, but it's bonded to a group 1 ion in this case, so we're going to say that it is soluble. And the last one, potassium hydroxide, again, normally it's insoluble, except when it's bonded to potassium, group 1. This is calcium hydroxide. Calcium, barium, or strontium. So there it is. Calcium hydroxide, the OH is bonded to calcium, and therefore it's soluble. And that's how you do it. So you break apart your compound into the cation and anion. Look for the anion. If you can find it, which side is it on, soluble or insoluble? If you can't, find your cation and look for that. And then check for the exceptions. The exception is always opposite of what it should be.